We have learned about set cover, we have learned about the problem shortest superstring, and we found a way to model it as a set cover problem. And now we want to relate the optimum solution of our shortest superstring problem with the optimal solution of the set cover instance that we created. There are two directions we have to look at. The first one is, how is the optimum solution of shortest superstring upper bounded by the optimum solution of our set cover instance? And the other one is the other direction. How is the optimum solution of the set cover instance upper bounded by the optimum solution for shortest superstring? We'll start with the first direction. And what we want to show is the following. We have an instance, shortest superstring. We know what the optimum solution is, or we know the length of the optimum solution. We have created our set cover instance, and we know what the minimum cost of this instance is. Then we can show that the optimum for shortest superstring is at most as big as the optimum of the set cover instance. How do we do that? In principle, we do the same thing as in the first part of the lecture when we analyze the greedy set cover algorithm. We assume that we know the optimum solution. We assume that we know the optimal set cover that consists of some superstrings pi I to pi k of the set cover instance. And from that, we want to create a solution for shortest superstring that costs at most as much as the cost of these. So we don't want to find the optimum solution for shortest superstring, but just some valid one. And we want to show that it does not cost more than this. If there is some valid solution that costs at most this much, then the optimum solution clearly also costs at most that much. So we get an upper bound from that. How do I build a feasible solution for shortest superstring from this set cover that I have here? Each set in the set cover corresponds to some superstring of two input strings. So we can create some string by just taking all these superstrings and concatenating them. So if we take pi 1, then pi 2, and so on up to pi k, then we get a superstring of the input. And what is the length of this string? The length of pi 1 is the cost of the set that corresponds to pi 1. And the length of pi k is the cost of the set that corresponds to pi k. So the total length of the string is just the sum of the costs of all these sets that are in our optimal set cover. This is also the cost of the optimal solution of the set cover problem. So this is a valid solution for our problem. The length of the solution is at most the size of the optimal set cover. And the optimal solution for our problem can have at most the length of S. So the optimum for shortest superstring is at most the length of the minimum cost of the set cover instance. This is the first direction that we need. In the other direction, we want to show if we have an optimal solution for shortest superstring, how large is the optimum solution of set cover. And for that, we can show that the minimum set cover of the instance that we create has cost at most 2 times the length of the shortest superstring. Let's try to prove this. Again, we start with the same trick. We consider an optimal superstring. We consider the optimal solution. We just assume that we are given it. And from this, we want to create a solution for the given set cover instance. Now this is a bit more tricky, so I will do it step by step. Assume this is the superstring S. The superstring covers all the input strings. So there has to be some string in the beginning of the superstring that is covered. And this is our string SB1. This is the leftmost occurrence of some string of the input set in the superstring. It doesn't make sense that the first character does not belong to any of those strings we want to cover, because then we could just make S a little bit smaller until we hit the first one, so it's not optimal. So we pick this guy here. This is our first string SB1. And now we want to go through the occurrences of all these other strings in S. So we walk from left to right. We look at the leftmost occurrence of another input string, which might be here. It might start at this point and it might end at this one. And then we keep going. What is the leftmost occurrence of another string? What is the leftmost of another string? Until we get to the last such one. So all the other strings that still are in S start to the right of this point. This gives us an interval, pi1. And this interval, as we can see, consists of the string sp1, and it consists of the last string that we found, se1. And they overlap somewhere in between here. So this is a string that we've defined before. This is one of those sigma strings. And the first index is b1 because we start with string sp1. The second is e1 because we end with string se1. And k1 is the number of characters where they overlap. Now we continue. From which point do we continue? We continue from the end of the first string. And we keep walking. Remember, so far we found all the strings that start somewhere in this interval from here to here. We still have to look at all the other strings that start to the right. So we take the next string that starts somewhere, and this is our string sp2. We do exactly the same as before. We keep walking through our strings until we find the last one that still overlaps with sp2. And this gives us the next interval. We start from here, the beginning of sp2, and we end at the end of se2. And they overlap in k2 characters. And we continue from here. We start at the end of sp2 and we keep walking. This is the first one we find. We walk through everything we find up to the last one, and we again get an interval. Now before we continue, we want to make one observation. And that is, if I look at this first string pi1 and the third string pi3, actually they don't overlap. Why is this the case? Why do these two strings not overlap? Look again at the order that we picked things. We started with the first string. This is the starting point of pi1. The string that defines the starting point of pi2 does not overlap with this first string. And this string sp3 does not overlap with the second one. So we know there's no overlap between sp2 and sp3. So the only way that a blue string and a brown string overlap is that one of them is very long and reaches over there, like this one here. But now, look at this string and look at the very first cyan string. Now the cyan string is included in this very long string. And in the beginning, without loss of generality, we assume that this cannot be the case. So we can show this way that there cannot be any string of pi1 and of pi3 that overlap. And the same holds for pi2 and pi4, and the same holds for pi3 and pi5, and so on. No two of these strings that are more than one apart can overlap. So we just continue with our construction. We pick the next string that does not overlap sp3, keep walking until we find the first one that does not overlap sp4, and so on until we reach the very end of the string. And now we have some overlapping strings here, and they cover all the strings on the way. Everything is covered by them. So every string of our input is a substring of some of these pi strings. And from that follows that the sets that correspond to these pi strings give us a valid solution for the set cover instance. And the cost of this solution is just the sum of the length of these strings. And we also know that no two substrings pij and pij plus 2 do overlap. So the only overlap you can have is between consecutive strings. And that means if we look at a very specific character of our string S, then this can only lie in at most two of these pi strings. So every character in our optimum solution of the superstring instance is covered at most twice by every set of the set cover. So the cost of the set cover is at most twice the length of the shortest superstring. And that means if we have some algorithm that solves set cover within some factor times optimum, then that also gives us an algorithm that solves shortest superstring within this factor times 2 times optimum. So with this reduction, we can again get an approximation algorithm for shortest superstring without ever really solving this problem, but with just reducing it to something else that we already know. So our algorithm is very simple. We construct the set cover instance as we defined before. We compute some set cover for this with our greedy algorithm. And from that, we again construct our superstring pi1 to pik. And this algorithm is a factor 2 times the harmonic function of n approximation algorithm. So this basically tells us shortest superstring is at most twice as hard as set cover. But again, is this the best thing we can do? Can we only ever get an order of log n factor approximation algorithm? Actually, yes, it's true, it's at most twice as hard as set cover, but it's really much easier. While for set cover we really needed order of log n and we cannot do better, here we can even get a constant factor approximation. In fact, the best known approximation factor is 71/30, or 2.367 so far. On the other hand, we cannot solve it optimally, and we cannot even solve it within factor 333/332, or we cannot get an 1.003 approximation algorithm. However, the gap between these two are really large. This is a really low upper bound, and it even took some time for people to get to this. It's very interesting how people arrive at these lower bounds. But there is a huge gap, and just pushing the bound in one direction from those two sides would be a huge improvement and a huge step in approximation algorithms. That's it for the second lecture. Thank you for listening, and I see you next week.